Welcome to the Deep Dive, the show where we really get into the details from the research crossing your desk. Today, we're jumping into computational fluid dynamics, specifically modeling Stokes flow.
Right, and Stokes flow, it's not your everyday water splashing. Think really slow, really viscous, like honey maybe, or flow inside those tiny lab-on-a-chip devices.
Creeping flow, they sometimes call it.
Exactly. Low Reynolds number. We're talking fluids where inertia is, well, basically negligible. If you stop pushing, it just stops instantly.
And that's critical for microfluidics, definitely, but also things like cellular biology, or even how oil seeps through rock, right?
Absolutely. And engineers trying to simulate this, they usually reach for the finite-element method, FEM.
Yeah, and the standard tool there, for ages really, has been the Taylor-Hood element. You know, P2P1, Q2Q1, those kinds.
It's popular, sure, stable, well understood mathematically, but, and this is the core issue from our source today, it has a major flaw for truly incompressible flows.
Incompressible meaning the fluid density doesn't change.
Correct. And for mass to be conserved in that case, the divergence of the velocity field, mathematically speaking, it has to be zero everywhere, at every single point.
So no fluid just appearing or disappearing anywhere in the system. Makes sense.
But Taylor-Hood, it doesn't actually guarantee that locally, pointwise. It might conserve mass overall globally, but inside the individual mesh elements, the divergence isn't zero. You get errors.
Which can lead to, what?
Yeah.
Phantom pressure drops, weird flow patterns.
Unphysical results, yeah. Things you really can't have when you're designing something super precise, like a microfluidic sensor.
Okay, so that sets up our mission then. We need to unpack this new approach, the hybrid formulation, which sounds complicated.
It is a bit involved, but the claim is it solves this local mass conservation problem, and it's actually more computationally efficient.
Better accuracy and faster. That sounds promising. How does it work?
Well, the big shift is moving to what's called a mixed formulation. We need different kinds of mathematical spaces for velocity and pressure. Specifically, Texet-Scherer spaces for velocity and 2002 spaces for pressure.
Okay, hang on. Hdiv spaces. What's special about them? Why not just standard polynomials?
Ah, that's the key. Standard elements, they often don't enforce continuity perfectly across the edges, the boundaries between finite elements. Text spaces are specifically built to guarantee that the normal component of velocity is continuous.
The component going across the boundary.
Exactly. Think of flow rate. So if you imagine your mesh like little connected pipes, make sure the flow out of one pipe section perfectly matches the flow into the next. That's how you get local mass conservation built in.
Okay, that makes sense. So Hdiv solves the conservation problem, but you said there was another headache.
Right. Hdiv handles the flow through the boundary, the normal part, but it doesn't force the velocity component along the boundary, the tangential part, to be continuous.
So the flow rate matches, but you might have like a mathematical slip along the edge where two elements meet.
Precisely. It's not physically quite right. So researchers first came up with the semi-hybrid formulation.
Semi-hybrid. Okay.
They used Lagrange multipliers to sort of weakly enforce that tangential continuity. These multipliers, physically, they represented the tangential stresses, the friction along the boundary.
But that led to computational problems, I gather.
Oh, yeah. A real mess, actually. It resulted in this large, complicated matrix system called a saddle point system.
And those are bad?
Notoriously difficult. They're ill-conditioned. They have poor spectral properties. Basically, they're slow and numerically unstable to solve. Accurate, maybe, but really painful computationally.
Okay, so semi-hybrid fixed tangential continuity but created a numerical nightmare. How does adding another hybrid in the hybrid-hybrid formulation make things better? Sounds counterintuitive.
It does, but here's the clever part. The second hybridization is about relaxing the continuity requirement on those stress functions themselves.
Well,
we let them be discontinuous. But then we introduce a new Lagrange multiplier. And this new one represents the tangential velocity itself at the boundary.
Wait, you swapped out one continuity constraint for another variable? How does adding unknowns simplify things?
Because of the magic trick? Static condensation. The specific structure of the equations you get from this hybrid approach lets you algebraically eliminate a whole bunch of variables before you solve the main system.
Eliminate which ones?
You eliminate all the degrees of freedom that are purely internal to each element, including those tangential stresses and the original Lagrange multipliers. You condense them out locally, element by element.
Ah, so the computer solves lots of small problems first, then assembles a cleaner global one.
Exactly.
Yeah.
And the final system you're left with only involves the velocity and pressure unknowns that live on the element boundaries. And this condensed matrix is beautiful. It's symmetric, positive, semi-definite,
Which means?
numerically stable, good spectral properties, much easier and faster for iterative solvers to handle. You trade upfront complexity for a vastly better final system.
Okay, that explains the hybrid name and the stability win. We've gone from a messy saddle point to a nice, clean, condensed system. Makes sense.
So that tackles the robustness. But what about speed? Often making something robust adds computational cost.
Which brings us to the second big finding, right? The choice of the specific HD space matters a lot for performance.
Yes. We're comparing two flavors, HEA-Day, the standard one, and Ye's Hdiv-C, which stands for constant divergence.
And why is Hdiv-C potentially faster?
It comes down to how many functions you need to describe the flow. Hdiv-C is pretty specialized. It's built using ideas from differential geometry, the de Rham sequence spaces.
Okay, deep math, but the practical outcome.
The key feature is that Hdiv-C uses significantly fewer basis functions, or shape functions, to get the job done compared to the standard Hdiv-S.
Fewer functions means fewer unknowns in the system, fewer degrees of freedom, or DOFs.
Exactly. Hdiv-C starts with a smaller system before you even do the static condensation. It's like starting a race with a lighter car, as you said.
All right, let's see the numbers. They did tests, like a 2D manufactured solution.
Yeah, where you know the exact answer. Even in 2D, Hdiv-C cut down the total DOFs by up to 40% compared to Hdiv-S.
40% is pretty good, but 3D is where things really get expensive computationally. They tested Annular-Couette flow between cylinders.
Yes, and that's where Hdiv-C really made a huge difference. In that 3D test, the reduction in DOFs was between 50% and nearly 60%.
Wow, cutting the problem size in half almost. That's massive for 3D simulations.
It's a potential game changer for performance, absolutely.
But the crucial question, if you're using, say, 60% fewer data points with Hdiv-C, are you losing accuracy? Is there a hidden cost?
That's the best part. No. The verification tests showed that despite using far fewer DOFs, the velocity solution from Hdiv-C had the exact same order of accuracy as the one from the much larger Hdiv-S system.
So all the efficiency gain with zero accuracy penalty.
That's what the results show. It's really the ideal scenario. Efficiency without compromise.
Okay, that's impressive. Let's shift to the verification then. Did the hybrid method actually deliver on that promise of local mass conservation?
Absolutely. They looked at the 2L-test2 error norm of the divergence. That's the key metric. For the hybrid method using either Hdiv-S or Hdiv-C, that error was down around machine precision.
Machine precision, meaning?
Like $10, $15, $10, $16, basically as close to zero as the computer can represent. Mathematically perfect local conservation. No artificial sources or sinks of fluid popping up in the simulation.
And how did that compare to the old standard, Taylor-Hood?
Stark difference. They ran the standard Taylor-Hood PDP-1 element, even on a fairly fine mesh, and the divergence error was around 0.025.
Which sounds small, but compared to 10 to the minus 15.
It's orders and orders of magnitude larger. It clearly shows that Taylor-Hood just doesn't enforce that local conservation property.
Okay, so proven. Locally conservative. What about the accuracy of the main results, like the velocity field itself or the stresses?
Also very good news there. When they compared the errors in the velocity and the deviatoric stress, the hybrid method actually produced slightly smaller errors than both Taylor-Hood PDP-1 and even the higher-order P32 elements.
So it's more accurate and locally conservative. Seems like a clear win.
It really does.
So with that kind of validation, they tested it on more realistic, complex problems, like those lab-on-a-chip devices.
Exactly. They threw some challenging geometries at it. A 2D channel shaped like a sine wave, a 2D serpentine channel with sharp bumps put in.
To really test the robustness near tricky features.
Precisely. And also a full 3D C-shaped serpentine channel, which is common in micromixers.
And how did it handle, say, the channel with the bumps? That sounds like a tough test for conservation.
It behaved exactly as you'd expect physically. Where the bumps narrowed the channel cross-section by half, the simulation correctly showed the fluid velocity doubling instantly to maintain the flow rate. perfectly conserved mass flow.
And it produced the right kind of flow profiles.
Yes, got the expected Poiseuille-like profiles in the channel sections and the characteristic pressure drops you see in these laminar micromixers. It shows the method isn't just theoretically sound, it works reliably in complex engineering type settings.
Okay, this has been a fascinating look under the hood of CFD. Let's try and sum up the key takeaways for you listening. This hybrid formulation really does look like a powerful, validated alternative to classic methods like Taylor-Hood for Stokes flow.
Yeah, I'd say there are three main advantages that stand out. First, that optimal local mass conservation. Getting the divergence error down to machine precision is huge for microfluidics and similar areas.
Right. Second, the cleverness of the double hybridization and static condensation. It transforms a potentially messy numerical problem into a stable, robust, symmetric, positive, semi-definite system that's much easier to solve.
No more wrestling with those saddle point matrices. And third, that synergy with the Hdiv-C space. Using Hdiv-C gives you a massive performance boost, especially in 3D, cutting potentially more than half the unknowns without sacrificing accuracy.
And looking ahead, this isn't the end of the story, is it?
No, the authors mentioned they're working on developing even faster iterative solvers, specifically for this condensed system.
Okay, refining the solution process.
And maybe even more importantly, they state this whole hybrid framework can be extended beyond Stokes flow to tackle the full Navier-Stokes equations.
So bringing inertia back into the picture,
Yep.
applying this to more general fluid dynamics problems.
Exactly. That opens it up to a much wider range of engineering applications where flow isn't quite so slow and viscous.
So here's the final thought we want to leave you with today. If you now have a simulation tool that delivers effectively perfect local mass conservation, that's something that's been a persistent issue in CFD, how does that change how you approach design? Think of designing those next-generation lab-on-a-chip devices, maybe for complex chemical reactions or biomedical diagnostics.
Yeah.
If your simulation truly reflects the physical reality down to machine precision for conservation,
Then maybe your reliance on expensive physical prototyping goes way down, if the simulation is that trustworthy.
could it fundamentally accelerate the design cycle? Something to think about.
Definitely food for thought.
Indeed. Well, that's all the time we have for this deep dive. Thanks for tuning in.